Thanks for coming, everybody. Today we've got sort of Marc Lelarge, who's visiting, as you know, it's the SCS program here. He's going to be talking about diffusion and cascading behaviour and random networks. So thank you very much.
Okay, thank you. So can you hear me, or is it working? I think it's not good. It is. Okay. Okay. I think it's for recording stuff. So if you can hear me, then that's fine. Though I did prepare some slides to present the result first, because I think it's easier to present them on slide, and then if you're interested into the proof, I did prepare some. I can show you part of the proof on the blackboard. Though I mean, it will be a quite interactive talk. So if you are bored with the results, just tell me, and I will go directly to the proofs. Okay. So just for a motivation, which is not coming from communication networks, this is coming from marketing. So I don't know if you. There is a famous book called Crossing the Chasm, and this is written by Moore. And he is saying that in order to market new technology, you have to market segment of the population one at a time. So you start with the innovators who will buy your, who are kind of geeks, and they will buy your new technology, whatever the price and whatever the performance. And then once you succeed with this first segment, you can start marketing early adopters, who are kind of high-tech enthusiasts. So it's not that hard, but then the big challenge apparently for startups is to cross what he calls the chasm. So it's to convince the early majority that your high-tech software is it's really of great value. And though you have to market each segment one at a time, and the big problem is to cross what he calls the chasm. And if you are looking at this way of diffusing a new application, you can use kind of standard epidemic model like SCR or stuff like that. And then you will not be able to see something like the chasm, though at least on uniform random graphs. So people have suggested that this the random graphs model are not appropriate for modeling such a diffusion, which might be the case, and this case might be due to clustering. And what I will try to look at in this talk is I will change a bit the diffusion, so the epidemic model, and see that you can obtain a threshold phenomena if you take into account what economists call neighborhood effects. So in the standard epidemic model, the probability that you adopt, say, the new technology is proportional to the number of people in your neighborhood who did adopt. Okay, so this is written like that. R is the fraction of people in your neighborhood who already did adopt, and you have a parameter alpha, which gives you the probability that you will adopt given the fact that you have R neighbor who already did. In this talk, I will consider functions like this. So these are threshold functions. So you adopt with probability 0 or 1. So it's a completely deterministic function. Given the fact that the threshold, the fraction of people who did already adopt in your neighborhood is bigger than the threshold or not. Okay? So if the fraction is low, then for sure you will not adopt it. And if the fraction is sufficiently high, then you will adopt. So actually this model can be seen also as a kind of mathematical modeling of this very simple game. So you have two technologies, ICQ and Google Talk. Okay, so I guess you all know what Google Talk or ICQ are. These are so when you are using Google Gmail, you can open a Google Talk window and talk with other people using Gmail. So basically, you can only talk with people using Gmail when you use Google Talk, whereas when you use ICQ, you can only talk with people using ICQ. Okay. So the first technology say you will receive a payoff of Q, and because I don't know, Google Talk is better, perhaps you may see video or stuff like that. the payoff will be bigger if you use Google Talk. And the bad thing happens when one of your neighbors is using ICQ and you are using Google Talk, and then you are not able to communicate, so the payoff is just 0. Okay, so this is a very simple game.
What is the game?
So the game is, do you want to use ICQ or Google Talk? That's it. So
There are two players? Or?
Yeah, well, in the initial game there are 2 players, and now I mean it's on this case it's not very interesting with 2 players, but let's do it on a network. So everybody is starting with the old technology ICQ, and then you say that the payoff of a node is just the sum of the payoff on with each of his neighbors. Okay, so the payoff of the guy in the middle is just q times the number of neighbors. Okay, so this one, he has 1, 2, 3, 4, 5 neighbors. So his payoff is 5 times q. And now say that you force a certain fraction of the population to use Google Talk. Then basically what does this imply? That this guy and this guy cannot communicate anymore. So you can remove all edges between blue and green vertices of the graph. And now you see that this guy, he lost 2 neighbors and he has only 1 left. So he will be much better off by switching to Google Talk. He will recover these 2 neighbors and just lose 1. So you see that he has an incentive to switch to Google Talk and to create these 2 new edges. And it can go on like that, and you have a kind of epidemics going on. And here the strategy is very easy. It's just you're computing what is your payoff when you are using ICQ and what is your payoff when you use Google Talk, and you take the bigger one and you choose either to use Google Talk or ICQ.
Sorry, and how these 2 people at the beginning starts with Google Talk? Because for them it was not good idea to use this.
Okay. So at the beginning, I'm forcing a fraction of the population to use Google Talk, and they cannot switch. So this is the model. This is a very simplistic model, and but this is just one way to motivate things. Okay, so here you have a very simple interacting particle system, if you want, where each node you have a Boolean variable, 0 or 1, depending whether you are using ICQ or Google Talk. Okay, so it's 0 if you are using ICQ and 1 if you are using Google Talk. And then you switch from the ICQ to Google Talk if the number of neighbors, so I'm writing it like that. So if you are node I, okay, you are summing over all your neighbors the number of people who are using Google Talk, and if it's sufficiently high, so bigger than a threshold that may depend on the degree of I, then you switch. Okay?
And you never switch back to...
No, I never switch back. So in this very simple case, actually, the function theta is just d, the degree, times q, where q is the parameter, the payoff when you are using ICQ, and 1 minus q is the payoff when you are using Google Talk.
So if you die, you die forever.
If you die, well, here you are not dying, but if you are switching forever. That's, yeah. So that's again, that's a very simple model. As you already mentioned, it's monotone, so you can you can define the finite state very easily for this game. Okay, given a network, you start with an initial condition, then there is only one actually final state due to this monotonicity property. And what I will be interested in is looking at the final state of this kind of epidemic on very large networks. Okay, so this is more or less the motivation. So what kind of networks I will be looking at? These are the standard random networks. I think Lelarge gave a presentation last week on random networks, so I guess you know a lot more than me on that. So this is the model introduced by Molloy and Reed, where you fix the degree sequence, and you put edges at random. So given the degree sequence, your graph is taken uniformly at random. Okay. So I will come back to this in more detail, perhaps in the proof. So if you want just have one example in mind, you can consider the random regular graphs. So you consider all graphs with n nodes on degree say 3, and you pick one at random uniformly among all possible graphs. Okay. And another case is a standard Erdos-Renyi random graph where you put an edge between two nodes with probability p divided by n. Okay, and you let n tends to infinity. So the regime I'm looking at, okay, for example, in the Erdos-Renyi graph is exactly this regime where p is a fixed constant and does not depend on n, right? So this is what physicists call the diluted case because the mean degree does not diverge as n tends to infinity. Okay. So in this case, actually, it's very easy to see that the degree will converge to a Poisson distribution with parameter p in this case and to a fixed constant in the other one. Okay. So in all maltalk, n will tend to infinity, and this parameter say will be fixed. Now the model I will look at for the epidemics is similar to the one I just presented, a bit more complex. So I'm just adding one step before the threshold percolation. I'm adding a bond percolation. So I'm removing some of the edges of the graph with probability 1 minus p. So this is, for example, to take into account the fact that two nodes did not interact during the period of time I'm looking at. Okay? So I'm just doing a bond percolation with this parameter pi. And then I'm applying my what I call symmetric threshold epidemic. So here again, when I'm node high, I'm looking at all my neighbors is this new graph with the bond percolation, which are active, so with a +1 here. And if it's bigger than a threshold, so this is a function of the degree of I, which might depend on the node high also. So in the previous case, this was a deterministic function, but you can take a random one if you want also.
What did you start from? You start from any such a good graph, and then you delete each.
So here it's completely independent from the graph structure. I'm just describing the dynamics of the epidemics.
Two-step procedure. You delete.
Yeah. So I'm first deleting some edges to take into account the fact that people may not interact during.
Independent of each other.
Yes. So this is a standard bond percolation.
Yes.
And then I'm doing this monotone. So actually I'm switching. I start with a seed of what I call active nodes. So I force some of these guys to be +1, and then I run the epidemics, the monotone epidemics I just showed you before.
No, I'm sorry, you started with a open graph?
Actually, yeah, I don't start either with, you start with whatever you want, the graph you like. You first do a bond percolation, okay? So you remove some, it removes some of the edges.
Why?
Because I mean, okay, you can take actually pi equal to 1, and this you have no first step. So this is just to take into account the fact that people might interact or not during the period of time you are looking at. So say you are looking on during 1 week, and you have say a social network of people, but you are not speaking with all your neighbors on the social network during that week. So you remove the edges that you did not use during that week. Okay? So this is the first step, bond percolation. And then you, with
So after that you just have what?
so after that you have a random graphs, no? Well, you started with yes, you have with perhaps different clusters. So it might not be connected anymore, but I didn't say I start with a connected one, though. I mean, I have still a random graph, and I'm doing my what I'm calling a symmetric threshold epidemic. So when I'm speaking with one of my friends, I'm asking him, are you using Google Talk or ICQ? And based on that, I switch to ICQ to Google Talk or not. Okay.
So the bottom action, see, yes, you do it before you're doing this.
Well, it does not matter actually.
But otherwise, sum of xi will always be 0.
No, I mean, you start the epidemic with this seed.
You will repeat the question again. What property of calculated graph will you use? Your original graph is anything, not necessarily lattice, not necessarily
Well,
regular
actually,
structure.
Yeah, so in what I will be studying, my starting graph will be that one. So actually, the bond percolation will only change the degree distribution in a sense.
Right, so for example, if you take average Cherny,
Then
You
this
already
will
have
change
randomness.
only the parameter p, the first
Yeah.
step. That's it.
so you already have randomness.
Yeah.
Then you superimpose percolation.
Yes.
That's what I'm puzzled about. What do you want to gain from percolation? More randomness.
No, that's just actually that's because if you take a threshold equal to 0, okay, then what do you obtain for this model? You take a general pi, but the threshold is 0. So you get infected as soon as you have one neighbor which is infected. So this is just an exploration process of your graphs. So in a sense, this is exactly a standard SIR model with a probability of contagion which is exactly pi. So this is what I want. So this model actually interpolates between the standard SIR model and what people call bootstrap percolation. But I mean, you are right that you are not gaining any generality with this pi. This is just a way of writing it. So this was exactly this slide. So if you take a null threshold, this means that you get infected as soon as one of your neighbors is infected, right? Okay. So in this case, the epidemic is just you are propagating a kind of virus with a probability which is pi, the probability that one edge remains in your first step, bond percolation step. So with the general pi on the threshold 0, you recover the standard SIR model. Okay. On the other hand, if you forget about the bond percolation, you have exactly what people call bootstrap percolation. So for a fixed k, you get infected as soon as the number of neighbors is bigger than the threshold. Okay, so this is one way to have a model in between the two.
That's the norm.
Yes, kind of. Well, the thing is, I show that you can analyze this model in only one shot, and you got the result from the SIR or the bootstrap percolation, depending which parameter you are taking.
But originally you said that if the portion of neighbors is larger than something, here you can calculate only the number of neighbors which is larger or smaller than something. But if the portion, you said originally that if the portion.
So I mean, this is because this function might depend on the degree node. So you can think of this as a portion. This is but if you forget this di, this is, and you take the same k everywhere, this is exactly bootstrap percolation on your graph. So this is a bit more general. Okay, so as you told me, you have a nice monotonicity property, meaning that since the seed will not switch back to 0, you can show that you have a monotone process in any finite graph. There is only one possible final outcome for the epidemics. Okay, so what I will look at are properties of this final epidemic. So I forget about the dynamics. I'm directly going to the final state of the epidemic. Okay, so here is the first result showing how you recover the SIR model. So you take a threshold which is 0. Okay, and this is a fraction of population with which you started the infection. Okay, So this is a plot for the standard Erdős-Rényi graph with this parameter. So this means that the asymptotic degree is 0.5, 1, and 1.5. Okay, the average degree in the graph. And what you see is that the curve, it starts at 0 for this case. Okay, and then there is an infinite derivative at 0 in this case, and it starts at a positive value for this case.
What's the axis?
So alpha is the fraction of the seed, the initial seed. Okay, and this gives you for 0.3 in this first model you end up with around 0.4 fraction of the population who got infected by the epidemics. Okay, so you know that this is the subcritical, critical, and supercritical case. Okay, meaning that in this case you have only small little components. So whatever you start with the alpha positive, you will infect only small components, and this is a continuous function as alpha goes to 0. Whereas in this case, you know that there is a start for well, take this one, you know that there is what people call a giant component. Okay, and even for a very small alpha, you will pick one guy in this giant component, and this is exactly the size. The limit when alpha tends to 0 of the giant component for the Erdős-Rényi graph. Okay?
So this is P equal to 0.5 or 1 point.
P equal to 1, yeah. So I'm just exploring the component of the Erdős-Rényi graph.
Equal 1, that's the expected number of connections.
Exactly. So I'm just looking at the exploration process. I'm trying to recover a basic result from a random graph theory.
Mark, start again. So assume we consider a red line. You start with P.
So the red line it corresponds to this first.
Okay. You start from how many seeds?
So the seed say is 0.1. So 1% of the population is infected uniformly at random on the graph.
Why it starts from 0, from origin? Why does your line start from origin?
So this is what I explained, because when alpha tends to 0, basically each guy that you will infect, you will have a propagation of the epidemics only on the cluster to which it belongs to. And when P is less than 1, these clusters are all very small. Okay? So when alpha tends to 0, you are taking less and less cluster, so the fraction of the population infected, the final fraction of population goes to 0.
What is alpha?
Alpha is the initial fraction of population infected. The size of the seed.
What is the theoretical status of this result? Are they proven?
Yeah, I mean, what I just the size of the component.
Yeah.
Well, for sure it's proved. I mean,
Well, what is the critical value of P?
1. I mean, at P equal 1, you have the derivative here is infinite, and then it starts. The value at 0 is starting to increase, and this value is exactly the size of the giant component. Okay, meaning that when you have a giant component, even if alpha is very small, for sure you will take one guy as the giant component and you will explore all these components. So the final state will be equal to the size of this component.
I don't know. I'm lost again. So you have infinitely many.
This is this is a well-known result, and this is another way to prove it. I mean, using this process.
Does it have a name?
This is Erdős-Rényi
Result.
yes, fast transition for Erdős-Rényi random graphs.
Okay. Repeat what are you saying. So you have asymptotics or what? For each alpha, you take any alpha.
So the model is as follows. You take your Erdős-Rényi random graph.
Yes.
For each vertex, you throw a coin with probability alpha. You put this vertex active, and with probability 1 minus alpha, you put it as inactive.
Yes.
And then you do the exploration process. Okay. So starting from this guy, you will explore the cluster to which it belongs to.
Yes.
So the GNP graph you've got, P is the mean number of
Exactly. Of
mean number
neighbor.
of neighbours. So P
Yeah.
equals 1 is the critical case, because that's
Yes.
the mean number of neighbours is 1. The number of neighbours is Poisson with parameter P.
P. Yeah.
Right?
Yeah. So I'm looking at that's
So P equals 1 is the critical case.
mean, what is difficult to grasp immediately
Sorry,
is that we are
sorry.
talking about the stationary measures, which is difficult to palpate, you know. So I do not see it, I do not feel that it's obvious.
No, I mean it's not obvious, but it's in accordance with a known result. That's what.
It was proven by Malloy and B.
No, I mean the Erdős-Rényi case. It goes back to Erdős-Rényi. Malloy and Reed did prove it for the configuration model. So the model, exactly the model I'm looking at, where you are fixing the degree sequence. Here the plot is just for Erdős-Rényi graph because I wanted just one parameter. But the most general proof is, well, under certain assumption of the degree, is done by Malloy and Reed. And here, this is one way to recover it.
So Mark, so what does this figure? What do these figures represent?
So alpha is a fraction of this. Is a fraction.
Alpha is an initial fraction. It's here.
Yeah, and this is a finite
And
fraction.
there is a finite fraction.
Yeah.
You didn't see it.
It's one fraction against the other.
The initial times 0 times infinity.
Okay.
You see.
So here is perhaps a more interesting result because I guess it was not proved before. So now I'm considering exactly the case of the game I showed you with one parameter Q, which was kind of quality of the software. So you are switching when more than D is your degree times Q. So you are looking at your fraction of neighbor.
Put inequality on the what I switch. Put inequality on the blackboard. You have so many blackboards around.
Okay. So it's some Q times DI, or if you want something like that. So you are looking at the fraction. So I don't remember if it's strict or not, but you are looking at the fraction of people who are active. Okay, you are dividing by your degree. And if it's bigger than Q, then you switch to 1, otherwise you stay at 0. And this is for the green line corresponds to Erdős-Rényi random graphs, where here lambda is the mean degree. Okay, and I'm looking only at for what value of Q will one single node trigger a large cascade. So meaning that with only one, starting with one individual, I have a positive probability that the final state is a fraction of the total population. Okay, so this is in a sense the same kind of thing as the giant component for Erdős-Rényi random graph. Okay.
So there are two lines on there, and there's a
So just look at the green one. Okay, so this lambda is the mean degree in your graph, and this is the value of Q. Okay, for which you have if you are
Where's the value of Q?
Q is abscissa. The y. So if you are below this, if Q is below this curve,
The graph is plotting Q. Okay.
sorry.
The graph is
This is a plot of Q.
Yeah.
The critical value of Q.
Yeah.
So for if the mean degree is 10, okay, if Q is in this range, then you know that only one guy can trigger what I call a global cascade.
Yeah.
Whereas where Q is bigger than this,
Yeah.
then you will for sure you will have no global cascade. Okay.
So you have a component which is fraction proportional to the total size.
Yes, that's it.
So just fraction is not non-zero.
Fraction, positive fraction.
Why does the graph go down at the left?
What is?
Why does the graph go down at the
Yeah,
left?
so that's exactly a good point. So here you see that it's starting to increase and then it's going down with the average degree, so which is kind of strange when you think in terms of a typical SIR model, because in SIR model, as soon as you get someone infected, if he has high degree, then he will infect more people. So it will tend to, the curve for the previous curve was monotonic in lambda if I would have drawn it. But here, what happened is that high degree nodes are hard to make switch. And when the degree increase, actually, you need a lower Q in order for this switching behavior to happen. So you see that here something, you have a kind of trade-off between the growth of the epidemic and the fact that in order to convince a high degree node to switch to the new technology, you will need a lot of neighbors. So it's harder to make him switch. And this curve is actually the same plot for power law graphs. So where you have a higher variance than in the Poisson case, and you see that this is much lower, the threshold is much lower than in the Erdős-Rényi-Warum graph. Yes?
You said something about what is the meaning of global cascade?
The global cascade is that with only one guy, I have a positive probability that the final fraction of people is positive.
Not zero.
Yeah.
Not one.
For sure, yeah.
Okay, so you start again. Here is the initial fraction of what?
No. This is the mean degree in your graph.
Mean degree.
Yeah.
A fraction, only one seed, yeah?
Yes.
And you start with only one.
Finite.
Yeah, finite number will work also.
So I miss what the red curve is.
So this is a plot for Erdős-Rényi-Warum graph. So when the asymptotic degree is Poisson, and this is a curve for power law graphs. So the variance in this case, this means that the degree sequence is power law.
Molly-Reed generation.
Yeah. So this means that the variance in this case for the degree distribution is much higher than here.
But
So
then lambda is the average number of neighbors
yes.
in a power law.
Yeah, a power law with finite, with finite mean.
With finite mean.
Yeah.
Okay.
But it might,
I still don't follow your intuition why
No,
it should then go
okay.
down.
So high quality means that the new technology has a higher quality than the previous one. So when Q is small, this means that Google Talk is much better than ICQ. Okay? So the lower Q is, the easier it will be to trigger a cascade. That's for sure. So, and this curve gives you exactly for what value it will trigger or not. So when lambda is, so if you have a mean degree which is 10, then if Q is in this range, then one single individual can trigger a global cascade, whereas if Q is bigger than that, then for sure the probability is one that you get a fraction. Well, the fraction will be small O of n.
Why is it continuous?
Well, this is just due to a threshold because I'm looking at this model. So you are counting exactly the number of people that. So you are increasing by 1 and minus 1. So that's.
Yeah, sometimes.
Yeah.
Now, this can be through triggers.
Yes. Yeah. So that's basically what I did. Then there is another question, which is what happened. So, okay, if Q is small enough, then you know that if you are a marketer, then basically if you need to convince just a few people, and you have a good chance to have a global cascading. And what happens if this cannot hold? So then you end up with so this is a plot similar to the first one, where alpha is a fraction of the initial seed. Okay. So here I'm fixing all the parameters. I don't remember which ones they are. So the green curve is the initial fraction of people who are active, and the red curve is the final fraction. And you see that there is a phase transition for a certain value of alpha. And well,
But the green one just it's out of
the green one is just identity. It's just a fraction of people who do. So
Could be larger. It's a similar graph, but you couldn't look.
No. Sorry.
So
This is
never
just
happens.
so the difference between the red and the green is exactly the people who you did not force to the new technology and who switch anyway. So the green line corresponds to people that you forced at the beginning to switch.
Okay. Yes.
So the red one is the final outcome. And you see that
What is alpha?
alpha is the initial proportion
Seed.
of the seed. Yeah. So you see that basically you are doing very little here, and then there is a huge jump at some point in alpha.
Still, I didn't. If alpha is the seed, what is the green?
It's just identity. So it's just f of x equal x.
Okay.
So
Okay.
the difference
Okay.
is what you gain.
In the
Thanks,
previous
very-
figure, alpha was 0 always, because you have 1.
So you,
Is that line vertical?
yes. The red? Well, there is a discontinuity. I mean, this is a plot with MATLAB, so but there is a discontinuity here. Actually, I don't know what happened exactly at the threshold.
Is this for another friendly graph? And do you get the same discontinuity
Yes.
for other graphs?
I mean, it does not depend really on the structure of the graph. So this phase transition. So this is actually what. So this is similar to what people study in computer science, which is called the k-core of a graph, and it's well known in this case that you have what they call a sudden emergence of the k-core. And here, similarly, when alpha reaches a certain threshold, then you have a positive fraction of the population who get infected. Here, actually, it's almost 1. So I think it's for regular graphs, this case. For regular graphs, you can show that it starts increasing slowly like that, and then it jumps to 1. Okay. I think I slipped. Do you want? Perhaps I should present a bit proofs then, and skip this part on the vaccination part. Or do you want more on result or more on proofs?
Proofs of what?
Well, just how I get the pictures. I just draw.
Pictures.
Yes.
Theorems behind.
So what is your hand?
Is it possible to formulate, to state what you're going to do?
Okay. Well, I want to. I put it here. I can state the theorem, and then, but it's gonna be a bit weird. Okay, so I introduce a function g of z, which is okay, so this function depends on the parameter of the problem, pi, and PSL is the probability distribution associated to the degree sequence with threshold L. Okay, so I can make this more clear. And so this is a function, g, which does depend only on the parameter of the problem. And you solve this this equation, and this basically gives you, so if h is a graph of active node, then you can show that the size, what I put, to 1 minus so if H is a graph of active nodes at the end of the epidemics, V of H are the number of vertices in this graph, then you can show that this, in probability, when n tends to infinity, the fraction of active node is given by this function. Okay? So either I can prove that or...
Okay, so I'm lost with notation.
yeah, but no. Perhaps
That's
okay.
what is the reason to prove?
So can you get the screen up? Thank you. Wow.
And you can prove it under your assumptions.
Yes, so I will put the assumption now. The conditions on the graph are the following. So I'm looking at the number of nodes with degree R, and this tends to a probability distribution. The mean degree is finite and positive. And I have a third condition. Okay, so here I'm using okay, I have a sequence of degree, di, which is given. So everything depends on n, but I'm removing it just for sake of notation. And this is the assumption I'm making on the sequence of degree. So if you are counting the number of vertices with degree r, this will turn to a fraction pr, which does not depend on n. Okay. The average degree for this distribution is finite and positive. And you need an assumption on the moment of the I. So if you are a probabilist, you can look at the random variable dn, which is just okay. So for a given n, dn is just the probability that your degree is r. So this is the number of vertices with degree r divided by the number of nodes. Okay, so this assumption means that this the distribution of this guy tends to an asymptotic distribution. So d with probability pr. Okay, this is the meaning of the first equation, and this is just to. Okay, yeah. So this is just to be sure that the mean of this guy will turn to the mean of this guy too.
You will not use your relation construction.
So the main thing is to construct the graphs on the epidemic model at the same time.
Condition triple I crucial for L1 convergence. It implies yes. L1, but it's sufficient. But is it necessary?
No, but
I'm just
yeah. Well, actually, I need that for something else, which is it's simpler to work on the graph di. So this graph is the multi-graph associated to this sequence of degree.
What is it?
The multi-graph. So what I'm really interested in is the simple graph associated to this sequence of degree. But it's easier to work on this multi-graph case, where you to each edges, to each vertex, you associate a bin, okay, with di balls. This is the configuration model used by introduced by Bobas and others. Okay, so you have a sequence of bins with balls in the bin. The balls correspond to half edges, and you want to make a graph out of this balls and bins process. So what you make is you take one ball here. Okay, you remove it from the bin, and you want to match this guy uniformly at random among all others. So you take one other ball uniformly at random, say for example this one, and you will put a link between these two vertices. Then you start with another with another ball. You pick another ball uniformly at random, so it might end up with that one, and you will end up with a self loop like this. So this is, or you may end up with multiple edges between vertices. So this is what I call G star. So under this condition, you know that everything that holds with high priority for this model of graph will hold for also this graph conditioned to be simple. Okay, so this is. You just need to work out this case, and you will with this assumption you have for free the.
Simple means connect.
The simple means that you know you don't have multiple edges on or self loop. And now the algorithm is just you will make this construction, and by the same time construct your epidemics. Okay, so the algorithm is as follows. You first. So here I'm just constructing the final state of the epidemic. So you remove all vertices from the seed. So S from the graph. And then you end up with a new degree, which I call di of A, okay, which is lower than the initial degree. Okay, because you remove vertices. And then what you do is you recursively remove vertices such that this new degree is sufficiently low. So the I of A is a degree of node I in this evolving graph. So what you start with is you remove the seed, and then recursively, if the degree is sufficiently low, you remove each degree I. So this can only get only lower, and you continue this inductive step until you are done. You are no more degree satisfying this condition, and it's fairly easy to see that you end up exactly the removed vertices are exactly the active nodes, and what is left are the inactive nodes. Okay, in this procedure. And now the game is to run this algorithm in parallel of the construction of the graph. Okay. So it's fairly easy to see that instead of removing vertices here, you can remove edges, where one endpoint satisfies this condition, and it will give you exactly the same result. Okay, so you have two types of node. So I will say it of types A if this is not satisfied. So if the degree on type B otherwise. So you are removing types B from the graph recursively. That's all what you're doing. So as I said, you can do it on edges instead of vertices. So and then you can do it on edges using this construction. So you start from your bins like that. Okay. So these are the bins, and you did not construct your graph yet. So the first thing you want to do is remove vertices from S, the seed. So let's say that these two guys consist of the seed. Okay. So at the beginning, I have type E on this on the left and type B on the right. Okay. And now I want to remove these guys. So I can forget actually about their bins. I just have to take into account the number of balls that are left. Okay. So this is the starting point of my algorithm. Now I want to know to which one this ball is linked. So I'm doing exactly the construction here. Okay, I'm picking a ball uniformly at random here. So say that one. Okay. I'm continuing like that, and perhaps it will remove that one, meaning that there is a link between a type B and a type A. And what happened in this case is that this guy, okay, you are always lowering the number of balls. So the number of balls is exactly this quantity. And at some point, it will be lower than this threshold. So, for example, if the threshold is 1 here, you have to move this ball into the set of B balls. Okay? So this is a kind of queuing process actually with two types, type B and type A. And you are removing balls like that. So you are constructing your graph at the same time constructing the final state of your epidemics. And so this is just a coupling argument actually. So everything from the probability point of view, this is only subtleties. And this is the main idea is due to Jansson and Malvina Luczak. Svante Jansson. They did that for the Ecole, a bit less general model. And now what you see, instead of removing balls, you can add colors. So by adding colors, I will say that each time I'm removing a B ball here, I'm coloring it red. I'm starting only with white ball. On B, I will color it red when I pick it not at random at the beginning. Okay? And now, if you look, A of t are the number of white A balls, and B of t is the number of white B balls. There is something quite easy to compute, which is this sum. Okay, if you are counting the number of white A ball and white B ball, what is this process doing? You are removing each time one B ball and one uniformly at random. So you can do it in continuous time. So how you do that is each time you recolor one of the B ball, you put an exponential clock on each ball, and the first one to click is the one you will associate with. Okay? So if you look only at white balls now, this means that you wait an exponential amount of time with the parameter g, where g is the number of white balls. Okay? So if you look only at the white ball process, you are removing them at rate 1. But each time you remove one, you actually recolor another one. So this is nothing more than a death process with rate 2. Okay? So this divided by n is just lambda, the number of perhaps 2 lambda, exponential plus I should write it like that. Okay, so this is just what you learn Divenko-Cantellis lemma. Nothing more. A death process where you have each ball has an exponential clock and it dies when the clock ticks. Okay, but here you are removing 2 balls each time. And there is another process which is simple to compute, which is A of t, because here you are not doing with colors. So you are just counting the number of beans with this threshold, and you are removing each white ball at rate 1. So A of t is actually given to you by exactly this process with z equal to exponential minus t. And this process is just b of t. So when b of t equals 0, which corresponds exactly to this equation, you have to stop the process and you did construct part of your graph on the epidemics. So this is the intuition behind this, this equation. So I guess I should stop here. So yeah.
What's the physical meaning of this parameter pi?
Pi? What do you mean by physical meaning?
Well, how to, I mean, when I see it, there are a few lines here. And it is possible, I suppose. Where is pi in the model? Is it the population?
Yes, that's the population at the beginning. Yeah.
But how? I still. Yeah, okay, it's in population, so it appears there. I'm sorry, but it doesn't appear in those conditions. Pi.
No. I mean, pi is just a fixed parameter. It does not depend on n. So I'm doing
so you do it for any pi.
Yes, for pi fixed, and that's. Pi is fixed, and this distribution does not depend on n either. Right? So that's on alpha. Alpha is initial condition that does not depend on n either. So
For every given pi between 0 and 1, those conditions will be fulfilled.
Yeah.
Are there any other questions?
Go quickly over the things that we didn't cover. Very quickly, just tell us what.
The thing, once you have this result of the final state of the epidemic given the initial condition, you can play with the initial condition. And what I did is I did look at, now you have in mind that the epidemic is a bad thing, like a virus or something like that. And you have, you are able to vaccinate people, meaning that from this graph point of view, you are able to remove people from the graph, meaning that they will not get infected and they will not propagate the epidemics. Okay, so this is, you are removing vertices from the graph. And I did study, if you have no information at all on the graph structure, what can you do? So the simplest thing is just you vaccinate people at random. Okay, and you see how it does affect the epidemic threshold, for example. So the curve I show you on the Q and things like that. And it turned out that it's not always very efficient, and there is another vaccination scheme which is much more efficient, which is what you want, at least in a typical SIR model, is to give a bias towards high degree nodes. So you want to vaccinate high degree nodes, okay, because they will propagate more the epidemic. So this is the intuition. So how to do that in a kind of decentralized way without knowing the topology of the network? There is a simple way to do that. Actually, it was proposed by physicists. So you pick a node at random, and instead of vaccinating him, you ask him for a neighbor. And then you vaccinate his neighbor, or her neighbor. And this will bias most of the time, the guys that you will take at random will tell you a high degree node, and this give a bias to the vaccination, which is actually very efficient for the SIR model and also for the threshold model. So you are able to actually compute the impact of the vaccination of the epidemics. And the game here is that since this result is fairly general and it's you can apply this on any degree sequence. What you have to do is just in the first step to see how the vaccination will alter the degree distribution. And then you can apply exactly this result and you are done. So it's really in two steps. You have first the vaccination and then the epidemics. And this is a simple way to... So the whole thing is to show that when you do the vaccination, you are still in this framework of what I call configuration model.
When you have this critical P, is it still decreasing when you have this vaccination procedure?
Yes, but for example, you remember, well, I mean, it's just lower this, you have this curve, and you will end up with a curve like that when you do the vaccination. So you are able to compute the gap between the two, or in the standard SIR model.
One more time.